All right, so I'm very happy to introduce our speaker today, Dr. Sash Sarangi from EM Alpha. He could explain to you what that name means. Sash received his PhD in theoretical physics from Cornell University. After postdoctoral work at Columbia, he has made a career move to quantitative finance and has done very well there. So in recent years, he has been interested in artificial intelligence as well as its interface with physics. So he founded a company called EM Alpha, which has become a leader in multilingual language model. So today he will tell us about thinking fast and slow.
Thanks, Gary. Great to be here. Nice to meet you all. So I got the first question before starting the talk, which is what's EM? Is it electromagnetism? And it's kind of funny. It really, depending on the audience, people come up with different interpretations of EM, which I think is a great thing, because what you don't want is the name of a company where people don't come up with any idea of what it stands for. When you make a company or a product, one is to make sure that you know the target audience pretty clearly, and automatically it should lead to what you're trying to tell them. So as Gary said, I was we both shared the same advisor. Gary was a few years senior to me. So when I moved to Cornell, Gary had moved on, and my advisor was Henry. At Columbia, I worked with Brian, and then I switched over to the financial industry just around subprime crisis. And I've spent, my career has evolved through, like a lot of physics folks, prior to big data, we used to start as a quantitative analyst. So I started as a quant, moved on to become a trader. I used to trade emerging markets, foreign exchange. Also, prior to EM Alpha, I was managing portfolios. Your retirement money sits in different sort of mutual funds, ETFs. So I was managing a number of portfolios at Invesco, which manages QQQ. You might have seen the word QQQ a lot on TV advertisements. So that was one of the ETFs we used to manage. So over time, I covered the entire life cycle. We call it the trade and investment management life cycle. So I was lucky enough to go through the entire life cycle. There are different words for it: front office, middle office, back office, et cetera, et cetera. EM stands for emerging markets. Alpha stands for, alpha basically stands for returns. If you look at the economics literature, alpha has a very specific meaning. People who take financial economics 101, one of the things they study is what is intelligent way of harvesting returns, what's a silly way of harvesting returns, and alpha has a specific meaning there. So it just means, investments, returns coming out of emerging markets. So very specific meaning, not relevant to this talk at all, but it has a very specific meaning for our clients. As I went through my journey through finance, I was one of the first users of AI in finance when I was in Boston working with State Street. Back in 2010 was one of the earliest applications of natural language processing to finance. So we used those models, we produced signals, and we traded on it. And like a lot of really good research ideas that are put into production or implementation, we immediately lost millions of dollars. So I have a lot of experience with taking the research ideas to practice and going through the bumpy ride as the research idea hits the ground. That's what, because of my background trading emerging markets of the world, everything from India, China, Middle East, Morocco's, Tunisia's of the world. I have a love and focus on emerging markets. There's a lot of fun that happens in emerging markets. Think about DeepSeek, think about coronavirus, think about tariffs, think about Trump's focus, think about the Middle East. A lot of the origins of what moves geopolitics is not sitting in the US or Europe, it actually sits elsewhere. And one of the fundamental problems I saw over the last 15 years was a lot of the information telescope of this world is focused on English language. Currently, only about 50% of the information on the web is in English. It's shrinking fast. Used to be 60% when I founded EM Alpha. Now it's 50%. The rest is in non-English languages. So the investors of the world, they're walking around one eye closed and trying to see what's in front of them. In the process, they suffer a lot. So the problem that EM Alpha has set out to solve, and we have made a lot of progress and have had a lot of fun in the process, is to develop truly multilingual AI applications that brings information from across the world to our users in a real-time way. So in that journey, we have different products that sit on different platforms currently. In this talk, I want to talk less about multilingual AI. I want to talk about one problem which has been on and off on my mind, like a researchy problem, and take that problem to go through the evolution of AI. The objective here is to entertain you. The objective is not to bore you with technical details. We will talk nothing about multilingual AI in this talk. So I don't know if any one of you has read Daniel Kahneman's book called Thinking Fast and Slow. It's a wonderful book. Kahneman and Tversky won the Nobel Prize for their research in behavioral economics. They've written a series of wonderful, wonderful books. And what they talk about is something very basic. The canonical example of that is the bat and ball problem. And let's see if we can move this. There you go. The bat and ball problem is very, very simple. Bat and ball together cost $1.1. The bat costs $1 more than the ball. How much does the ball cost? And you guys immediately have answers in your brain. And turns out that when you ask this question to the general population, pick randomly 10 folks on the street, they get the answer incorrect, right? Because they say 10 cents and $1, obviously. That sounds like reasonable. And you are a physics audience, so I'm not going to bore you with this question. I'm going to bore you with a different question, which is, why is literally my favorite question for anyone who claims to know physics when they want to interview with my team is, why is the sky blue? And I think any physicist who doesn't have the answer for that question does not qualify to be a physicist. I honestly believe that. Because when you're 10, I have a 10-year-old, he asked me, why does the airplane fly? Why is the sky blue? And I'm in the science force in my son's elementary school. So I go and parents do a lot of science experiments. So kids ask these questions. And I feel like this is something we owe to them to know these answers. And a lot of times you actually come up with, physics teacher style new answers to old problems. But as you all will immediately say, sky is blue because of Rayleigh scattering. And that's an immediate answer, right? And when you want to go a little bit more in detail, why is the sky blue? Then what does Rayleigh scattering mean? Well, blue light scatters more, right? And then if I'm not satisfied still, or my son is not satisfied still, you're going to go a layer further, and you can keep going on and on. It's Rayleigh scattering, blue scatters more, and it goes as the fourth power of the wavelength. But as you're going through this entire sequence of logic, your brain is slowing down, right? So what happened is your brain tends to think in terms of heuristics, where it says sky is blue because of Rayleigh scattering, right? We're not even thinking, we're just saying that. Of course, that's when you're sitting for your grad school viva, immediately Gary says, That's why sky blue. You're gonna shoot him with, why are you boring me? It's blue because it's Rayleigh scattering. But your brain didn't think through the whole thing. To think through the whole thing, it gets really slow, right? That's the entire thinking slow and fast process. And we go through that journey a lot as we do our research, our day-to-day living, because without thinking slow and fast, there's no way we can make progress through thinking, right? And you can go on and on. I kind of went off and why is the sky not violet? And you can have a lot of fun with that question. Again, the question, well, actually, the reason I think very carefully about it nowadays is for a slightly different reason. Has any one of you ever done day trading? You've done day trading? Okay, excellent. So what happens with, let's look at the motion of S&P index. It's been extremely interesting and exciting. Thanks to Trump, life is interesting and exciting. And you see that in your retirement portfolios and in the day-to-day movement of S&P. This is from last Friday. A lot more has happened since last Friday and today. The S&P fell on Friday. This is showing you the 1 minute price price action, and it fell 100 points. That's a whopping almost 2%. On over a period of what? Over a period of 2 hours, right? And look at, if you're a day trader, you care a lot about these price motions. And each one of these is driven by something that's going on in the market. So on Friday, the jobs data came out. If you guys were looking at news this morning, it actually has swung up the other way because another data point came out this morning about 2 hours ago. But this price action happens minute to minute, second to second, fraction of a second to fraction of a second. So if you're a day trader, you are waiting here at 8:30, 8:29 a.m., click, 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 8:30, something happens, and you better act here and here. Otherwise, you've lost your gains, right? So the Citadels and the jump tradings of the world, they do a lot of this, right? They're acting second by second. And even though it might look like noise here, there is a lot of pattern to it. There's a lot of story to it. Fed, Jerome Powell spoke at 12:30, and then something very interesting happened. Things are happening very fast for day traders. Now, let's change the frame a bit. Let's look at what happened from mid-December till today. Again, Trump gets elected, S&P rallies, people go crazy. They're like, oh man, the world will be beautiful and rosy. So the S&P keeps rising, rising, rising. When something happens, Powell puts, cold water on the market crashes 3%. That's insane. And then up, down, up, down, up, down. For a medium frequency trader, there's a lot going on here. And as you're making an AI system, doesn't matter whether it's a transformer model, a ChatGPT, an Anthropic model, any AI model, they must develop an understanding and narrative to it. Go to ChatGPT and ask these questions, right? Today, after the talk, hey, can you explain to me what happened from mid-December till today? Give me 5 bullet points, summarize for me that market action, right? And see what it says. And then ask it questions at different time scales. And then this is something, going to the next slide here, you can look at the past multi-years. Of course, coronavirus, this is 2023 post-corona, market went up. This is the AI rally. Again, a lot of structure to it, to the trained eyes. All of these are really interesting stories which happen for very specific technical reasons. This is not noise. This is a lot. Every single slide I showed you, while it might look like noise, there's a lot of interesting story there. So what I've spent a lot of my 10 years is trying to come up with how does machine learning and AI look at this information? Not just price move. Price move is the final output of stories, narratives, data, and numbers. This entire S&P price action is driven by what happens in the White House, what's going on in the brains of the population at large, what's happening with GDP data, what's happening with inflation data. So there is text, there's numbers, a lot of drivers here. How do you make sure that an AI system puts it all together and gives you an understanding of this price action? And again, there's thinking fast and thinking slow here. So multiple examples where the brain or an AI system should think on multiple time frames to come up with an understanding of a phenomena. Now, let's see how the AI models have addressed this question over the last 20 years and how that has led to the development of AI models. All right, so let's begin with how many of you know about LSTMs? So I figured some of you, half of you know LSTMs. So the entire purpose of, if you think about it, the stock market example that we just spoke about, that's a classic example of this kind of problem that LSTM should be able to solve. Long, short-term memory. You want to persist some sort of memory, and you want to forget other kind of information very, very quickly. And as you guys know, it's the main difficulty in maintaining long-term memory is the problem of vanishing gradients. And this is the fundamental problem that has been solved by LSTMs, by transformers, or by the DeepSeeks of the world in various different ways. And why does the vanishing gradient problem happen? The vanishing gradient, at the end of the day, it doesn't matter what neural net you are looking at, you have to minimize some or optimize some sort of a loss function. And how do you optimize the loss function? You change the different layers and you look at how the loss function is changing. That naturally leads to a chain rule. As you shift one layer, that moves the next layer, that moves the next layer. And the problem is that leads to vanishing gradients because of what? Because of sigmoid functions, right? At the end of the day, every single neural net operation that involves some sort of a sigmoid function, as long as you are dealing with sigmoid functions, the derivative of that is something that looks like this red line. Details are not important at all. Doesn't matter if it's a sigmoid, tan, hyperbolic, ReLU. At the end of the day, you have these two sort of configurations. And when you multiply a lot of these red lines, which are the derivatives, as you jiggle you're taking the different layers and looking at the change in the loss function, that gives you zero. At the end of the day, that's what the vanishing gradient problem is. And do you guys know why the sigmoid function, typically they tend to choose this particular feature for the transformations?
I mean, the Railer doesn't do it like that, right? The Railer does it this way. I would say the Railer is a little more common now than the segment. But I think for the segment, the idea is to, I mean, you want to have bounded results, so you have to squeeze them in something. And so you have some dynamic range that, which is in the middle. If you put something in this dynamic range, then you have some variability, and the other two sides are sort of clipped off if you want.
Right. It's you want to give a sense of probability distribution, some sort of a cumulative distribution function, because doesn't matter what sort of observations you're looking at, you want to give it the characteristics of a distribution function and a sigmoid or a ReLU, like whatever function you want to come up with, that at the end of the day is, if you think of this red line as some sort of a central limit theorem distribution, then the cumulative distribution function is the blue line. And you can come up with different sort of, ReLU is somewhat different, but at the end of the day, you're taking some sort of observations of the world, a lot of observations of the world, and you're saying, let me transform it to some sort of a probability distribution. And when you transform anything to a probability distribution, it tends to have this robust sort of, cumulative distribution function tends to have this sort of feature, right? Like Gaussian, cumulative Gaussian, etc. But that basically is a very robust reason why you have the vanishing gradient problem. And again, seems like half of you guys have gone through this in previously, but when you look at these models, in this case, you're looking at an attempt to build an LSTM, and you come up with ways to predict the next word in a sentence. Because of the vanishing gradient problem, it tends to forget what has already been fed to the neural net, right? So if you're saying, I grew up in France, I speak fluent something, then by the time you get to something, it's already forgotten what was fed to it before because of the vanishing gradient problem. And the way you solve it is you add a long-term memory, which is the memory cell, which is C1, C2, C3, C4, etc. here. So at the end of the day, what you have done is, you had these hidden layers, which is the classic textbook example. You have these hidden layers in a neural net. Let me add memory cells, which have it's like the most simplistic way you would think of solving this problem, right? Without even implementing it, you would say, well, I know what the problem is. The problem is that the hidden layers have this instability of the vanishing because of the vanishing gradient problem. By fiat, let me add these cells C1, C2, C3, C4, which don't have that problem, right? Without giving anything about the implementation. That's the first thought that comes to mind. Then, of course, someone says, okay, so your hidden layers are the short-term memory and your cells are the long-term memory, but how do you make sure there's a long-term memory? And if you read that paper, that original paper always confused me. It was like, because they give you the answer first in terms of gates and long-term memory, the cells and the hidden layers, which are short-term memory. And I was like, where does all this come from? So this is my reconstruction of how they must have thought, which is first think of a long-term memory. Obviously, that will solve the problem by definition. And then you say, well, what is the most simple thing I can do to have a long-term memory? Then, well, the most simplest thing you can do is, again, go back to the basics. The hidden layers are just some sort of sigmoid functions. At the end of the day, that's all the hidden layers are doing. The long-term memory has to be something which is not a sigmoid function, right? Actually, let's be really dumb and let's say it's a linear function. Whatever your brain thought here, just carry it on here, just carry it on here, just carry it on here. Let's just say that's possible. And if you could implement that, that would solve the problem. And that's what they did. And there is a hidden, you still have some neural net thing going on here, which is sitting in the FT. That's what they call the forget layer. So the idea is actually very, very simple, which is keep the layers, the hidden layers, the problematic, forgetful hidden layers that were in the textbook examples. Add this persisting layer, which of course, if you have CT minus one, it should be CT, the memory cell. C stands for the cell. And come up with the way, the f of t, which decides whether you should forget or not forget. If you don't want to forget, f should be 1. If you want to forget, f should be 0. This is as simple as it gets, right? And then the fact that you want this to be 0 or 1 or something in between should make you think again of sigmoid functions. So it turns out when you look at the final implementation, this is also a neural, this f of t, which forgets or doesn't forget, that is also a kind of a hidden layer. It's a neural net layer. There are a couple of more variables here, which are, I don't think they are important at all in the fundamental understanding of LSTMs. This encapsulates the entire idea of LSTM. Now, when you think about, well, how do I make sure that f of t does the right thing? You will be forced to come up with 2 additional variables, the input and output layers, but those are somewhat extraneous in the way I have understood LSTMs. So this is how you would go to bed every night and be like, I don't forget LSTMs ever. This is my understanding of LSTMs. And when there are 3 or 4 different, there's a peephole LSTM, there are like 4 or 5 different LSTMs that came up, which are more of engineering reasons. But this is what I would call the physics understanding of LSTMs. Now, again, look, this linear C means there is no sigma distortion. There are no derivatives of sigma or ReLU going over and over again, which prevents the vanishing gradient problem. And what you have done is basically now you have a long-term memory and a short-term memory. So it was a really simple, beautiful solution to the long short-term memory problem, which led to the discovery of LSTMs. How much time do I have? Okay, good. Now, so that's great, but as many of you might know, there is the good thing about LSTMs is they solve the long-term memory problem. It always reminds me of that Jim Carrey movie back when I was in grad school, Eternal Sunshine of, you guys remember, for some reason, LSTM always reminds me of that movie because it's about persistence of memory, right? The bad is, it's a sequential way of doing things. So you are stuck with sequential. So when I was a kid, someone told me this entire trick about speed reading. And how do you do speed reading? Speed reading trick is you look at a piece of paper. You don't read the words word by word. You don't go like, I grew up in France, I speak fluent French. At least purportedly, the trick is you stare at the page, your eyes somehow look at different sections of the page, and they absorb the different sections and kind of process different parts of the paragraphs in one shot. Now, that's something that parallel processing cannot be done in LSTMs by construction.
Out of curiosity, did it work for you, the speed reading?
It never worked. I think it's a scam. I think it's a scam.
I've tried it to a complete failure.
Yeah, I know. It was very frustrating. I was 12 or 13 or 14, right? Preparing for all these college exams. I was like, this is what will take me to the MITs and Harvards of the world. It was a complete waste of time. But luckily for us, AIs are able to speed read. And Transformer is basically a speed reading technique for AI. And again, now I think it's become, because of the AI revolution, feels like even my kid knows what self-attention is. It's basically the speed reading trick. Instead of reading word by word, line by line, you break down the input information into different sections, and you parallelize the entire process. So There are two different things that go on here, which is self-attention and the multi-head processing, which makes these transformers extremely powerful. Again, we are the thread here is thinking long-term and short-term. So LSTMs was one way to solve that problem. Transformers are another way to solve the same problem. And DeepSeek is yet another way to solve that problem, right? And in all of this, the long horizon and short horizon is coming in because one of the biggest problems with AI was the problem of context. And the problem of context is all about thinking slow and fast, thinking long and short at the same time. That's what context, after all, is all about. Now, in one slide, what transformer does is they're different. So if you look at the paper, it's that entire architecture is, at least I always find it very confusing. So for me, the simplest way to understand what the transformer does is you have your input information that gets converted into word embeddings and position encoding. You do need a position encoding here because there is no more feeding off the information word by word by word, first word, second word, third word. Therefore, you need a way to encode the positions of the words. And that's it. That's the preparation, right? So you prepare your information with these three steps, and then you have self-attention. You're looking at the information in one shot. You're looking at the entire page in one shot, right? So that is the self-attention. When you're asking a transformer a particular question about a body of text, it's not looking at the body of text word by word by word and predicting the next word. Rather, it's paying attention to the entire body of text to come up with the answer. And then you have, after self-attention, you have with the polishing of the output, you have feed-forward layer, you have further normalization and the final output. Why do you need these layers? Because those of you who have really spent a lot of time looking at these word embeddings, etc., they tend to be somewhat unpolished. They have these different kind of there are numbers in those vector embeddings where you don't really need those numbers. So think about multidimensional vectors for each word. And based on the context, you might have sort of noise for certain entries. Do we really need that noise in words to make your transformer really powerful? You don't need those kind of edge noise things. So when you're doing the polishing, you're getting rid of the numbers, small errors, small numbers, etc. At the end of the day, that's all you're doing. But the entire fundamental breakthrough here was self-attention. The multi-head concept is important because you have a lot of cases when the same word can have somewhat different meaning. When you say, Gary went to the bank, do you mean the banks of your lake here? Maybe he got so frustrated with day-to-day life, he's about to jump into that, which he'll never do. He's one of the most optimistic folks I know. Or did he go to the bank, hopefully to get some money to feed me dinner tonight, right? Which bank are we talking about? And that's where you want to have the multi-head attention step, because based on the context, the words can have different meaning. Finally, and we are moving to the last part. Again, for me personally, the problem in my mind is really long-term, short-term. What's going on? How do you solve the stock market problem? Thinking long period, short period at the same time, it's a very difficult problem. So again, LSTMs is one, transformers is other. Again, there are problems with both of those. LSTM is sequential. It's very hard to do parallel processing. They get very onerous, very, very heavy, difficult to maintain, difficult to one of the fundamental differences between a research and trying to come up with a product is cost. OpenAI is hugely loss making. And they are funded by VCs, so they can do a lot of research, but it's not clear whether they will go bankrupt or they will become a successful business. So when you're thinking about that problem, you have to think very hard about, well, what are the different ways to solve this problem? What's the most cost-effective way to solve that problem? And how do you build a successful business? So in that context, again, LSTM is one way to solve that problem. Transformers is the second way to solve that problem. And then those of you who watch Amazon Prime a lot, then you might have seen those advertisements, Matthew McConaughey and AI agents. Has anyone of you seen those advertisements? Okay, all right. Clearly, I watch a lot of Amazon Prime, but however, are you guys familiar with the word AI agents? How do you define AI agents?
Let's say something that interacts with the world.
And it's fuzzy, right? Like the agents word is everywhere, but then when you ask, even I like, go and ask Sam Altman, what's an AI agent? He's probably going to say it's a fuzzy concept, because again, the entire field is developing very fast. So agent, I challenged someone to come up with the simplest example of AI agents. And he did that. And he also came up with what I personally believe is one of the simplest Python codes to implement AI agents. It's very beautiful, very elegant, something that undergrads or even high schoolers can write. So AI agents are, these are systems, AI systems, pieces of code, which take some input that are able to look at the evolving output and polish the output based on some criteria of, is it good enough yet or not? Is it good enough yet or not? And then stop automatically by deciding, oh, it is good enough now. Again, there's no external interaction in that definition. No one is going and running the loop for loop and deciding when to stop. The AI agent decides this. That's one definition of AI agents. But generally, when we are talking about AI agents, what we are thinking of is different AI modules. It could be OpenAI is one part of it. Some other Anthropic system is a second part of it. And yet another model is a third part of it. And all of these modules are working together to solve the problem. And that is where the AI industry has aggressively moved over the last 1 year. And again, that I really like that architecture, because then you separate out the long horizon thinking and short horizon thinking to two separate systems. You free yourself from the constraint of thinking only within the confines of one model. You're not thinking only LSTMs, you're not thinking only transformers. You could think some combination of those two. And DeepSeek did that. DeepSeek was one of the first implementations of that idea. I think a lot of folks were thinking in that direction. DeepSeek just happened to be quick and smart enough to do it very quickly. Again, I'm sure you guys have followed all of this. DeepSeek, it came up with the Coder, then V3, and finally R1. Why did DeepSeek really come up with this breakthrough? If you ask me, there were cultural, organizational reasons, as well as technical reasons. Technical reason is never the only reason for breakthroughs. Usually there's also an organizational reason. And the organizational reason is very simple. Big tech was forced. It's been addicted to a lot of money. When there's a lot of funding, you go for bigger models, you go for really ambitious projects. whereas DeepSeek was basically a quant shop. Quant shops are always, they can never compete with the Googles and Apples of the world. So they all continuously come up with quick and dirty ways of solving problems, any quant shop. So that's in their DNA. And they used to do high frequency trading, a bunch of quick and dirty way of doing things. And they took it to solve the AI problem. And but so I think that organizational problem, the reason is very, very important. And then they had limitations because of the ban on the chips, which, I think that it ended up helping them. On the technical side, there are two directions they took, which were very powerful. One was the mixture of experts, and the second one was reinforcement learning. The mixture of expert idea was simply that, this is something motivated by our brain. If you look at our brain, it's a big, big, messy neural net. But when it comes to specific tasks, only certain parts of it get involved in those specific tasks. And that's exactly what DeepSeek did in this is straight out of their paper. Based on the particular problem they are trying to solve, they only invoke certain parts, certain experts sitting in their entire neural net architecture. There can be one part of the neural net, which is always, the big boss that's always shepherding the smaller experts. And then there are specific task-specific experts, which might or might not become active based on the problem. Again, the mixture of expert idea has been around for a long time. They also use the idea of distillation. Over the last couple of years, a lot of folks have been thinking about I think they've also implemented a bunch of these. We certainly use distillation at EM Alpha. You have a large language model, which is the teacher model, and then you have small language models, which are very specific to given tasks. In my day-to-day life, our AI looks at foreign exchange, it looks at stock market, it looks at bond markets, and there's no reason to use one large language model to solve all the problems in every single financial industry. So we have one set of models that looks at stocks, another set of models that looks at foreign exchange, and then there is a teacher model that orchestrates all of this. This is where you're moving to cost-effective, low latency, and more scalable way of doing things. This really is where the entire industry has aggressively moved. You'll see a lot of this sort of architecture going forward, where a large language model is driving an entire team of small language models. By the way, this is how, if you talk to a lot of experts, this is how AI is revolutionizing workforce, right? Previously, you used to have a manager that, or even now, there's a manager that handles the smaller team of expert workers. The entire idea is just replace that way of planning the organization with these AI architectures.
So what's missing would be if there are problems that require different types of creativity, then you miss the correlation. In the brain analogy, there are different parts of the brains that are useful for solving a problem, then this smaller language model will not be able to find the correlation.
Yeah, so the idea would be, do you want to just have like static smaller language models, or do you have a way to dynamically evolve the language model, right? Because there's the training part and there's the inference part. And when we think about these models, we think of these two in separation, right? That, okay, this model was trained on this corpus and that's it. But you can make that entire process dynamic. And which is how our brain itself evolves, right? That's how it learns. So that's very interesting, right? Like we are continuously learning in our life. Whereas if you think about a lot of models, they learn, they're trained, and then we use their whatever knowledge they have been trained on to ask questions. But the training stops there, but it doesn't have to. You can make that entire process dynamic. Again, that's with large language models, it's infeasible. Right? That's extremely expensive. You train them once and then you use them for inference. But with the new architectures, if you have a bunch of different small language models, you can start thinking of doing that in cost-effective ways. And the large language model can just be, can decide how much further and when that training of the small language models has to happen. Just out of curiosity, have any of you played around with small language models? Okay, awesome. All right, so going back to the stock market question, the way we try to solve that problem is we have literally a bunch of different small language models, long horizon expert that doesn't care about what's happening minute to minute or hour to hour in the markets. Then we have a medium horizon expert that looks at hour to hour price movements, and then a short horizon expert that looks at second by second movements in the markets. It's a very powerful way of solving. There's no way you can do this in like go try asking any of the GPTs out there minute by minute question. They can't do it just because there's no way you can train it real time and get inference real time, right? They're pretty effective up to a few hours, but not second by second. So to solve real-time problems, you need these small language models that are working together in an AI agentic architecture. And then I will end with Mark Anderson's $1 trillion questions. It's a super exciting field, and there are a lot of really important open questions. I stole it shamelessly from the latest Lex Friedman podcast where he talked about these $1 trillion questions. Where is the entire the dance between big models and small models going? Where do you want to use this separation between large language models and small language models? This is extremely crucial for solving problems, business problems. Then, with DeepSeek, the question about open versus closed models, right? What's the future of that? Training data is a real big problem. A lot of the AI has now, a lot of the web has information that is being spewed out of AI. So how do we get real training data? So I've noticed that there are these firms out there that reach out to grad students or PhDs for training their AI on physics problems. When some firm is training an AI on solving physics problems, it's like, who's going to train those AI models? They reach out to grad students, or I certainly got reached out by recruiters. They were like, hey, do you want to solve for our AI these high school or college problems from Res McCalliday? I did that for a couple of days. I was like, this is pretty cool. I can still solve these problems. But they literally have these PhDs that train the AI models to solve physics problems, but that's not scalable. How are you gonna, like, there's no way you can scale that process up. So that question about synthetic versus real training data. Then, DeepSeek again showed you that you can use non-supervised reinforcement learning to come up with a chain of thought during inference. So that's going to be super interesting. And then there are other questions about policy, censorship. Is there an AGI? And so all of these, I think, month by month, year by year, you'll see some big developments on all of these fronts. So with that, I'll stop and take any questions. Yeah, you do that.
I'm curious about your thoughts about state space models, because I think or something like predicting the stock market or any kind of like, yeah, thing where you're gonna have much like mixed Fourier modes, I would expect a state space model to do really well. If people, I assume people are doing this. Do you have any thoughts on it?
People have definitely looked at those models for quite some time. In economics literature, people have studied regime changes when your market volatility changes suddenly, or macro, think about the markets today versus a year from now when everyone was feeling great. They have used state space models to solve those problems. With all of if you want to compare those models, so let's be a bit more general, right? So there are machine learning approaches to solving financial problems, and there are these Gen AI driven approaches to solving problems. The question you can ask is, which one is more powerful? Which one is leading to better results? And the answer, according to me, is a combination. There is a research article by Harvard folks that looks at, they basically make the point that don't just throw away your old machine learning methods to chase Gen AI, because what will work really well is a combination of the two. What happens, so think about, let's take a step back. Think about linear regression, right? Linear regression, even now, is an incredibly powerful way to solve finance problems because it doesn't overfit. It's really simple. You don't overthink every decision. But the problem, that precisely also is the problem, because thinking in terms of the long-term and short-term charts we looked at, your linear regression would say, well, the market's been going up for 2.5 years. It should keep going up. Now you would try to make it richer by adding, you can add state space problems or decision trees or whatever you want to use. But at the end of the day, when you think about how a day trader thinks about these problems, a day trader always is going back and forth between long horizon, short horizon, long horizon, short horizon. The best day traders can do that very, very, very quickly, which means that, think about your classic machine learning methods or linear regression as a way of doing long-term thinking. They're really good at long-term thinking. And think of Gen AI as something that brings in short-term thinking. So after every decision step from the linear regression, you would say, is there something that Trump tweeted over the last 1 hour that this linear regression model might be missing? Generally, that's how linear regression gets screwed, because, well, it doesn't know what is being tweeted right now. So I think at the end of the day, to really what I'm trying to say is, it doesn't matter which model you're looking at, that it's less about the specific problem or the specific model, but it's more about the paradigm shift. I think the paradigm shift is simply Gen AI provides you a very robust way to combine different models together. Until now, that was very, very difficult. It was very difficult to say, look, I like that part of the linear regression model. I love this part of the hidden Markov model. I love that part of bag of words NLP approach. They are all solving different problems. Let me combine them all. That was very hard to do. It was like juggling 5 different balls at the same time. You could do it for a few seconds and then you drop the balls. With Gen AI, or the large language, the big versus small dancing together, now you can orchestrate them. And that really was not possible until now.
So how do you make them interact, the large model and the many small models? Are they sending like text messages, or are they?
So they're different. I think people are actually coming up with different architectures. I do have a big tech team that's really good at doing that. So what they do is they use different in- have you heard of WebSocket.io module? These are different modules, HTML, to pass HTML messages back and forth. So what they do is you could, go on Amazon Cloud or Google Cloud and just sign up for 5 different small language models and 1 large language model. And they are all sitting in different containers, let's say, or different machines. And then you can have different protocols like WebSocket.io is one way to do it, to pass messages among themselves.
And they're like clear text messages, like human readable messages.
Yeah, you could, it doesn't have to be human read. That's entirely up to you how you do it. But if you have humans involved there, you would have human readable messages. But at the end of the day, these are all like HTML or TCP/IP. That's one way to do it. But at the end of the day, you could have even if you have one Python code, right? In the same Python code, you could have a call to a large language model and calls to small language models and just pass that information back and forth between them, right? So it really depends on how you want to do it.
Are you training these models on time series? Are you more just doing inference of them, or are you actually fine-tuning them on time series from financial data?
Yeah, no, that's a great question. So one thing I completely did not mention in this is we end up spending a lot of time in prompt engineering. And what we have found is we end up needing a lot of economists and traders and quants to do the prompt engineering. Without that, these models, especially the large language models, they are very good at.
I know the next talk has begun, so everybody should come in. Yeah, go ahead. No, come.
The large language models especially are really good at generic reasoning. But once you get to specific reasoning, you need domain experts to do prompt engineering. And then you have meta prompts, and you can have prompts at more of a meta level. Again, think about boss prompt and worker prompts. So you have to do that whole dance between the prompts. That takes up a lot of time. Yeah.
There's another talk now. So
Yes.
many of us have meetings with you later, including myself. I don't know who else, but Sash is around. But
Yeah.
Okay.
All right. Thank you, everyone.
Thank you.
Thank you.
You have to end the meeting.
Yeah, I thought about it.
So it's always thinking fast and slow approach. So you assume that there's certain decoupling between like what's happening on short scale and long scale.
Yeah.
Is it always the case?
No, it's not always the
So
case
how
at
do you
all.
facilitate the interaction between
Right.
short scale, long scale models?
Right.
Yeah.
So that again would come down to, so that's a really hard problem. And I don't think anyone has solved, I think people could write papers on that. But the way we try to solve that problem is by, again, doing prompt engineering and telling the models that if the intraday, so let's think in terms of price movements, right? So when the day-to-day price move is within 0.5%, usually nothing big has happened. But so you can simply, to your small model, you could say, if the price movement is greater than 2%, hold on. There is some really major shift going on in the market. If a major shift has gone on in the market, then has the